All right. Good morning, everybody. Quickly, let's move into what we have today because we already lost about 4 minutes. Now we are starting with Faraday's laws of electrolysis. Okay, if you recall last week, that's where we are going to start from today. Faraday's laws of electrolysis. Now, before understanding Faraday's laws of electrolysis, let's recap the process of electrolysis that we looked at last week. Now, I said from the study that we had last week, I told you something that whenever an electrolyte, like let's say for example metal sulfate, okay, whether it's calcium sulfate or hydrogen sulfate, is diluted in water, the molecules split into positive and negative ions. Trying to refresh so I can understand Faraday's law. Okay, these molecules split into positive and negative ions. Now, the positive ions, which are actually the metal ions, the which are the negative. I said the positive ions, which are actually the metal ions, move to the electrodes. It moves to the electrodes connected with the negative terminal of the battery. We understand. I think we remember that. And then for the negative electrode, it moves. Sorry, I'm trying to connect my phone, my laptop. It just got light now, so I'm a bit distracted. All right. So I said whenever an electrolyte, like for example, metal sulfate or hydrogen sulfate or whatever, once they are diluted in water, the molecules of the the metal, the metal sulfate will split into positive and negative ions. So I said the positive ions, which are actually the metal ions, move to the electrodes. Okay, which is actually remember the electrodes are connected to light, to a battery terminal. Okay, so the positive ions, which is the metal ions, move to the electrode that is connected with the negative terminal of the battery, while the positive ions take electrons from it, becoming a pure metal atom, just like we described the electrolysis of brine water last week. And once this is done, once they take up electrons, they become pure metal atom and they get deposited at that electrode. Why the negative ion, which is usually the sulfur ions, move to the electrode that is connected to the positive terminal of the battery. Remember what we did? And now these negative ions, they have to give up their extra electrons to become sulfates, or more or less like the radicals. They become free radicals by the fact that they gave up the extra electrons that they have. And now, since they cannot exist, since these radicals, these sulfates cannot exist in an electrically neutral state, what happens is that it has to attack the metallic positive electrode in order to form a metallic sulfate, which will again dissolve in water. Okay, so we've explained all these things. I'm just trying to, recap on what we did last week, so I'll be able to understand the Faraday's law of electrolysis. Now, when we talk about Faraday's laws of electrolysis, there are basically two things that comes to mind. Number one, we said Faraday is actually the person who came up with these laws of electrolysis, and it's purely quantitative. Okay, Faraday's laws are purely quantitative because it shows a mathematical relationship, okay, that exists during electrolysis, both at the positive electrode and also the negative electrode. Now, these laws assert that the amount of substances liberated at the electrode depends on three factors. So, according to Faraday, he said for substances to be liberated, the amount of substance that will be liberated at the electrodes, whether the cathode or the anode, depends on three factors. Now, these three factors, we have the magnitude of the steady current passed. So, what's the magnitude of the current passed? What's the time of flow of this steady current? And what change will the ions have on the elements as liberated? the change on the ions of the element liberated. Those are the three factors, okay, that this law tends to tell us, okay, in order to determine the amount of substances that will be liberated at the electrode. I said the magnitude of the current that is passed, the time of flow of the current passed, and then of course the change on the ions of the elements liberated. So let's look at Faraday's first law of electrolysis. It says that the mass of substance liberated at an electrode during electrolysis is directly proportional to the quantity of electricity passed through the electrode. The mass of substance liberated at an electrode during electrolysis is directly proportional to the quantity of electricity passing through the electrode. Now, from the explanation that we've already had, I just explained to you now, the electrolysis that we've been having, that electrolysis, from the explanation of what happens at the anode and the cathode. Now, it is clear that the flow of current through the external battery circuit fully depends upon how many electrons get transferred from the negative electrode or cathode to positive metallic ion or cations. That is this factor that I was talking about, okay, which is the magnitude and the amount of this current that is being moved. Now, let's say, for example, now, if the cations have, for example, valency of 2 ions, example like copper now, copper has 2 valence electrons in the outermost shell. So if the cations have valency of 2, like that of copper, then for every cation, there will be 2 electrons transferred from cathode to cation. Okay? Now, of course, we know that basically for every electron has a negative electrical charge of 1.602 times 10 raised to power 19. Let me break it down so that I don't get too fast, and I want us to understand what I'm trying to say. Now, I want to use this phenomenon to explain Faraday's first law of electrolysis, where he came up with the idea that the quantity, the amount of the mass of substance liberated at an electrode is directly proportional to the quantity of electricity passed. That's what I want to explain. I said, if, for example, based on those factors that Faraday told us that determines the amount of substance that is being deposited on the electrode. Now, I said, if, for example, you have a metal that contains 2 valence electrons, like the copper, okay, then for every cation, there will be 2 electrons. Those 2 electrons must be transferred from the cathode, okay. Now, like I said, now for every electron that is being transferred has a negative electrical charge of 1.602. Write that down. Every electron has a negative electrical charge of 1.602 times 10 raised to power 19. 1.602 times 10 raised to power 19 coulombs, which is usually written as minus E. So whenever you see minus E, it means it has the electron has an electrical charge of 1.602 times 10 raised to power 19. So for the position of copper atom now, okay, on the cathode, there will be 2E, because the copper contains 2 valence electrons. Okay, so 2 electrical charge will be transferred from cathode to cation because of the 2 valence electrons it has. Now, let's say, for example, now the second one, which is the time. So I've explained the magnitude of the steady current. Now, the number 2 now is the time of the flow of this steady current. Now, let's say, for example, now the time for T, which is time, there would be a total number of copper atoms deposited on the cathode. There will be the time with which these copper atoms are deposited at the cathode. So total charge transferred will be 2Ne, because that N now represents the total number, okay, of copper atoms that is deposited or at the cathode. So the mass of this copper deposited is obviously a function of the number of atoms that is deposited. So it can be concluded that the mass of this deposited copper is directly proportional to the quantity of the electrical charge that passes through the electrolyte. That is where this Faraday's first law came from. Okay, so that's why we said that Faraday's law, first law, states that the mass of substance liberated at an electrode. Remember, this mass, okay, depend on the valence electron that this metal had, okay, has. So the mass of substance that is liberated at the electrode during electrolysis is not directly proportional to the quantity or the amount of electricity that is passing through it. So hence, mathematically, you have that M is directly proportional to Q, where M is mass, Q is the quantity of electrical charge that is passing through the electrolyte. Okay, now remember that Z is always constant, a constant proportionality. So by the time you have that M is directly, you know the sign of directly proportional. Mathematically, if you have M is directly proportional to Q, where Q is equal to M. So we can now have that M is equal to ZQ, and the Q and the Z is a constant proportionality. This is known as the electrochemical equivalent of the substance. So mass is directly proportional to the quantity of electricity that is passing through it. Equation will have that Z is equal to M, which implies that the electrochemical equivalent of this substance is the amount of the substance deposited on passing one coulomb through the solution. So if you pass one coulomb of electricity, the mass of the substance that will be deposited will be dependent on this one coulomb that passed through the solution. So that's how Faraday came up with the first law of electrolysis. Now, the second law of electrolysis, it states that when the same quantity of current is passed through different electrolytes, the relative amount in moles of the elements deposited are inversely proportional to the charge of the ion of the respective element. Okay, it states that when the same quantity of current is passed through different electrolytes, the relative amounts in moles of the elements deposited are inversely proportional to the charge of the ion of the respective element. Now, what does this mean? Let me explain it. Now, so far, we have learned that the mass of the chemical now, okay, which is deposited due to the electrolysis is directly proportional to the quantity of electricity that passes through it. That's the first law. Now, the mass of this chemical now, which is deposited due to the electrolysis, is not only proportional to the quantity of electricity passed through the electrolyte, because further study that Faraday carried out as far as electrolysis discovered that there are other factors too, not only the amount of electricity or the quantity of electricity that passes through the electrolyte determines the amount that will be deposited. There are other factors, okay, that this is also dependent upon. So now say that every substance will have its own atomic weight. Remember, every substance, including that copper or whatever, they have the atomic weight. So for the same number of atoms, different substances will have different masses. We know that already. Now again, how many atoms now are deposited on the electrode will also depend upon the number of valency, which we've already established. Now, if the valency is more, then for the same amount of electricity, the number of deposited atoms will be less. Okay? But if the valency is less, the same quantity of electricity, okay, will be more. Okay? Will be more, which is deposited, which is the number of atoms that will be deposited on the electrode. So for the same quantity of electricity or a charge that is passing through different electrolytes, the mass of the deposited chemical is now directly proportional to its atomic weight and inversely proportional to its valency. That gives us that second, because now Faraday did not just pay attention to only the amount of current that is passing through the electrolyte determines the amount of substance that will be deposited. Now he also paid attention to the atomic weight of that substance that is being deposited. And that's why he came up with this electrolysis, that the atomic weight of the substance also affects the number of the amount of the substance that is being deposited at the electrode. So that's why he came up with the second law, that the mass of the deposited chemical is directly proportional to its atomic weight and inversely proportional to its valency, which is the valence electron that it has in the outermost shell. So when you put the Faraday's first law and second law together, you have what we call equivalent weight, the chemical equivalent or the equivalent weight, which is actually given as the atomic weight divided by the valency. So if you want to calculate for the chemical equivalence, okay, after an electrolysis, the formula is usually given as atomic weight divided by the valency. Okay, like we know, the person who invented these laws is Michael Faraday. Okay, in the year 1934, that was when he came up with this. That's when he published these laws, Faraday's laws of electrolysis. Now, Faraday is a well-known scientist. There are other laws that he also discovered outside the laws of electrolysis. He's responsible for popularizing terminology such as the electrode, the ions, the anodes, and the cathodes. Even in ionization, Faraday also played a whole big role there, even in hydrogenation. So he has done a lot of work as far as science is concerned. So what are the uses of electrolysis, not electricity, please? The uses of electrolysis. What are the importance, or what are the uses of electrolysis? Number one, there is extraction of reactive metals. Extraction of reactive metals is one use of electrolysis. Extraction of reactive metals. Now, metals that have high reactivity, like sodium, calcium, magnesium, aluminium, they are all extracted by their ore by electrolytic reduction. We have already explained that. If you look at the electrolysis of brine water, which is sodium chloride, you will see that sodium as a reactive metal is being produced from that electrolysis, that electrolytic reduction that takes place. Okay, so they are being extracted from the ore by electrolytic reduction. Now, these metals cannot be reduced using carbon because carbon is less reactive than them. So what happens is that you can only get them through electrolytic reduction. And electrolytic reduction talks about passing electrolytic current through the molten state of this metal ore. As soon as electricity is passed through the solution, this metal solution or this ore, it brings about the metal is actually being produced from it. Okay, so metal being positively charged is deposited over the cathode. So sodium, okay, is not deposited at the cathode, and the sodium is the metal. So that's how you're able to get sodium from the brine, from that solution. Okay, so already gave example of electrolysis of sodium chloride when we said when electric current is passed through a molten state or solution of sodium chloride, sodium metal is deposited over the cathode, and I gave you the reactions and everything. Now, these metals that are obtained from this process of electrolytic reduction are pure in form. So you see that one of the ways we can actually get, one of the uses of electrolysis is extraction of reactive metal. The assignment that I gave us, the CuSO4, you also see that copper is also being manufactured, extracted from that electrolysis. Okay, so that is number one use of electrolysis. Number two, I'm going to put electroplating as a second now. Let me talk about purification of copper. Electrolysis helps in the purification of copper. Now I'm going to explain that. Now remember that we already said that. Now these metals, okay, that are extracted from various methods contain some impurities. Copper is one of those things. For sodium, it's not a problem because what is being gotten at the after the reduction, the electrolytic reduction, is a pure metal. But the other metals that are being produced and still have some impurities in it, we also use electrolysis to also, purify these metals. Example, especially like copper, for example. Now, what happens is that, let me just give you a background of how this is done. Now, first of all, when these metals, after being extracted from various methods, may contain impurities. Okay, so they have to now, they need to be refined. In order to remove the impurities, they need to be refined so that we can get the pure metal in a process called electrolytic refining. So to remove the impurities from these metals, especially copper, it needs to undergo what we call electrolytic refining. And what is electrolytic refining? In the process of electrolytic refining, now a lump of this impure metal and a thin strip of pure metal are dipped in the salt solution of metal to be refined. Okay, if for example I want to refine this copper, for example, you have to dip a lump of impure copper. Let's say for example copper, now I have to dip a lump of impure copper metal and a thin strip of pure copper into a solution of copper sulfate. So the impure copper metal and a thin strip of pure copper serves as the electrodes for that electrolytic refining. Now, while the solution is the copper sulfate, now what happens is that once you pass electricity, the impure lump of metal, okay, which is actually connected to the positive pole, then the thin strip of pure metal is connected to the negative pole. Now, once electricity is passed, electric current is passed through the solution, the pure metal from anode moves towards cathode and is deposited over there. As the pure cathode migrates to the cathode and is deposited there, while the impurities present in the metal are settled near the bottom of the anode in the solution. Okay, now these settled impurities in the solution are called anode mud. So easily, once you bring it out, you cannot get your pure metal from the cathode, while the impurities are already settled at the mud. So that is how electrolysis is also used to purify copper. Okay. Number three is electroplating. Okay. Let me explain electroplating. How you can also use electrolysis to do electroplating. Now, basically, we know corrosion. We know what corrosion is about. Now, most of the metals we have on planet Earth keeps on reacting with atmospheric air. Most metals keep on reacting with atmospheric air. Now, once they react to this atmospheric air, it leads to the formation of a layer over the metal. Okay, now in a long run, when this keeps occur, you may not see it at first, but after a long period of time, these underlying layers of the metal, okay, will keep on getting lost due to the conversion into oxides and sulfides of carbonate. Okay, I'm giving an example now. Now, as a result of this, now the metals get eaten up. This process refers to as corrosion. So when the metals keep reacting with atmospheric air, okay, after a long period of time, it will start eating up. Okay, remember they are already converted. If, for example, now it's copper. When copper reacts with oxygen, which is the atmospheric air, oxides are formed, which is the copper oxide or copper sulfide or copper carbonate. Okay, now when these copper oxides are formed, it will start eating up the metal. And as you start seeing that the distance will start corroding, to start breaking off, That's corrosion. It will break off because of what? This reaction, this continuous reaction of these metals with atmospheric air that leads to the formation of oxides, carbonate, and sulfides. And all these things have the ability to eat up the metal. That process we refer to as corrosion. Now, another thing that we also need to understand is what we call rusting of iron. Rusting of iron. Now, I've explained corrosion of iron, which is as a result of the reaction with the atmospheric air. Now, for iron, now rusting of iron is very, very common form of corrosion, but that's the first thing you will notice before corrosion takes place, before the metal gets eaten up, rusting first occurs. Now, when When this iron now, for example, comes in contact with moisture present in the air, which is water, okay, the upper layer of the iron turns into iron oxide. When this iron comes in contact with moisture, a combination of water and a little of oxygen, okay, the iron oxide is actually formed. Now, this iron oxide is usually brownish red or reddish brown in color. That reddish brown coloration you find on ions is referred to as the rust. Now, this phenomenon is called rusting of iron. So that brown red coloration you find on iron is actually rusting, and that's as a result of what the reaction of iron with moisture. Now, if this rusting is not prevented in time, the whole iron article, that's the whole iron, will turn into iron oxide. Once it turns to iron oxide, when the whole iron turns into iron oxide, it is referred to as corrosion of iron. So rusting of iron gives huge loss every day, both in our homes, industries, and the rest of them. Now, how do you now prevent rusting and corrosion? It is a process called electroplating. So you do electroplating to prevent the rusting of this iron and corrosion of these metals. Okay, so use electroplating to actually do that. How do you do electroplating? How do you do electroplating? Electroplating is basically the process of plating one metal onto another by hydrolysis. Okay, the process of plating one metal onto another by hydrolysis, basically either for decorative purposes or to prevent corrosion of that metal or iron. That is all referred to as electroplating. There are different types of electroplating. We have the copper plating, we have the silver plating, we have the chromium plating. So this electroplating allows manufacturers, okay, to use inexpensive metals like the zinc, steel for majority of the products. So how is electroplating done now? Let me just briefly, describe it because it's not part of what we're supposed to do. But let me just explain how electroplating takes place, how it is done. Now, the cathode during the electrolysis now, as we said, one of the uses of electrolysis is electroplating. The cathode will now be the piece to be plated. So the cathode is what we want to will contain, the cathode will be what we want to electroplate or want to cover up to avoid rust and the corrosion. While the anode would be either a sacrificial anode or an inert anode, normally either platinum or carbon. Okay, and these two, the platinum or carbon, must be in form of a graphite form. Okay, now sometimes plating occurs on racks too, okay, or barrels for efficiency. Okay, so these in oil companies, for example, they use a lot of pipeline, so electroplating is very, very important there. So now what happens is that by the time you now use the cathode, let's say for example, this you want to do, let's say for example, you want to spoon, for example, you want to electroplate the spoon. The spoon will now serve as the cathode, while, for example, the silver anode, the silver will act as the anode. Now, during electrolysis, once electricity is passed, remember that silver, okay, will lose its um, extra valence electron, and then they are being transferred to the cathode containing the spoon, okay, and they are being deposited at the silver is being deposited on the at the cathode, which is the spoon. So that's how the spoon gets electroplated. Okay, so the electrons are transferred from the anode containing the silver to the cathode, and once it goes there, the spoon will now undergo will now be covered with this silver. That's how to do electroplating. So anything you want to electroplate, use it as a cathode. Then introduce that what you're going, the material that you want to use to do the electroplating, that will now form the anode. Once electricity is passed through it, it passes through from the anode to the cathode, and then it becomes electroplated. There are different types of electroplating, like I told you. And the purpose, like I said, of electroplating is for appearance, to make it shiny, for protection, for special surface properties, for engineering or mechanical properties. Those are different. And then for the production of chlorine, of course, everything I've been discussing since, like that sodium chloride, the brine water, you also see that chlorine is being produced from that brine water, okay, through the electrolysis of brine water. The same thing also for the hydrogen sulfide, hydroxide, and sodium hydroxide. All these are, so the product, the main product of the electrolysis of brine water is the sodium, while the byproduct, okay, is the chlorine. Okay, if you're doing the electrolysis of hydrogen tetraoxo sulfate 6, the main product of that electrolysis is the hydrogen, okay, while the byproduct is the hydroxides, okay. So to produce chlorine, hydrogen hydroxide, and sodium hydroxide, it is also through the electrolysis, because they are also the byproduct of that. So chlorine can be manufactured by the electrolysis of sodium chloride solution, okay, while the production of chlorine results, the co-products are usually the sodium hydroxide, okay, which is the caustic soda, and also the hydrogen gas. Okay, these are things that are being produced as byproducts during electrolysis. So we can use electrolysis to produce chlorine, hydrogen hydroxide, and sodium hydroxide. Okay, so let's proceed. So that's that for the Faraday's laws of electrolysis and the uses of electrolysis. So at entering principles of catalysis, I'll be looking at the rate of reaction as a continuation of electrochemistry. So I'll just introduce it because I have 4 minutes left. I'll introduce it. By the time we'll come next week, we'll build it up from there. So basically, catalysis is the process of increasing the speed or otherwise changing a chemical reaction with the aid of a catalyst. That's catalysis. The process of increasing the speed or otherwise changing a chemical reaction with the aid of a catalyst. And we can all define what catalyst is. Catalyst is any substance, okay, that when introduced in a chemical reaction will speed up the rate of that chemical reaction without itself undergoing any chemical change. So catalyst is any substance that is used to speed up the chemical reaction. So they're introduced to the reaction, they help to speed it up, but they don't undergo any change. You can also get your catalyst at the end of that process. So that process of speeding it up, chemical reaction, by the introduction of a substance to speed it up or to change the chemical reaction, is what referred to as catalysis. Okay, and this, we said, this can only be done with chemicals that will already react together, and is used in research and industry to accelerate the reaction. So that catalyst must be able to react, okay, but it's not part of the reaction, but the only thing it does is that it helps to speed up the chemical reaction, okay. And then the cause of this phenomenon is that catalysts require a less activation energy or the minimum energy to initiate a chemical reaction. So when we come to the rate of reactions, we'll be looking at all those energy, activation energy, the enthalpy, the entropy energy, and the rest of them. So we're going to be discussing that in our next class. Then we'll also look at the working principles of catalysis, and then we'll look at the types of catalysis, and then we'll build it up from there. So we're going to be stopping here for today, and then when we come next week, we'll continue. But I also want us to write a short note, because what I just did here, I explained it, okay? So that in case if you get this in your exams, I can ask in exams and briefly explain, okay, list 4 uses of electricity. Briefly explain at least 4 uses of electricity. so that I don't just list it. Even as I've given it to you now, you expected to go and, from my explanation, use it to form your notes. We go and research on this thing. Talked about extraction of reactive metals like the sodium. When you do electrolysis of brine, sodium is the main product. Production of chlorine becomes the byproduct. So you build your note on that. Electroplating to avoid rusting of ions and corrosion of metals. And for any iron or metal you want to electroplate, you want to plate, just use it as a cathode and then introduce that substance, okay, that you want to use to do the electroplating as the anode. Once electricity passes through it migrates, okay, to the cathode and they're deposited. Once they're deposited, you just plate that iron or that metal that you want to do. And of course, I explained purification of copper and the rest of them. So we'll be starting from principles of catalysis next week, and hopefully we'll build it up from there. Thank you so much for your time, and I'll see you next week.